All right, so tonight what we're going to be learning about is balancing chemical reactions. And this all goes back to the concept of the very first unit with the law of conservation of mass, which stated that mass can neither be created nor destroyed. So what it translates to when we have a chemical reaction is if we start with a certain amount of magnesium, we need to end with that exact same amount of magnesium. If we start with a certain amount of sulfur, we need to end with that amount of sulfur. We can't go up or down. And as a result, what we need to do is we need to take into account all of the atoms and make sure they're the same on both sides of a reaction. Meaning whatever we start with as far as our reactant counts go, we need to end with the same amount of that atom on the other side as far as our products go. There are a few hints that you're going to need to become familiar with as far as when you are expected to balance a chemical reaction. And what that is first you want to keep your polyatomics together. So anything on that ion sheet, you want to keep them together as far as your counts go. It's not mandatory. These are once again just hints, but this does tend to make a lot of the calculations easier. Okay? And you only want to do that if you see a polyatomic on one side and it's the same polyatomic on the other side of the reaction. You want to balance oxygens last and then hydrogens second to last. Okay, so any other order, it really doesn't matter. So if I have a magnesium and I have a sulfur, it doesn't matter which one you go with. Okay, but oxygen you always want to balance last, hydrogen second to last. And the other hint the last hint that I know of is that if you have water on one side of the chemical reaction and you have OH on the other, sometimes it's beneficial to write out water as HOH. And now that OH as a part of the HOH, this is now a polyatomic ion of hydroxide. And so you would keep that unit together. Okay, so this sometimes helps you out when you have water on one side and hydroxide on the other. So let's just go straight into balancing. The first thing that I like to do is I like to write down all of the elements that I've got, and I write them all underneath this arrow, okay? Then I start doing my counts. So counting, you have to count however many you have. So on the left side, I have 1 magnesium starting, and I have 1 magnesium on the right of my arrow. So we've got our products, and we've got our reactants, and we're going to do our counts. Sulfur, if I look at sulfur, I have 1 on the left, and I have 8 on the right. Okay, and as far as iodine goes, I have 2 on the left and I have 2 on the right. So what I'm going to want to do now is I need to make sure that everything is balanced. So if I start with 1 magnesium, I need to end with 1 magnesium. So magnesium seem to work because I have 1 and 1. Sulfurs, on the other hand, do not. I have 1 and 8. Iodines, I have 2 and 2, so those seem balanced. So how do we change it? Well, the only thing that you are absolutely allowed to change in any of these chemical reactions is you are only allowed to change the coefficient. This particular number, which will be large, is called the coefficient. Okay? The coefficient is basically going to be a multiplier, and what it does is you multiply that large number and you distribute to all of the elements that are found in that particular compound. So you want to figure out what is the least common multiple, and between 8 and 1, it's 8. So how would I get this side to equal 8? Well, what I would need to do is put an 8 in front of here, which would distribute both, making my magnesium 8, okay, because it would be 8 times the subscript, which is 1 for magnesium. And then I'd multiply the 8 by the S, which has a subscript of 1, which would change that to 8. Now, my S's are balanced, my I's are still balanced, but my problem now is that magnesium is no longer balanced. So what's the common multiple between 8 and 1? Well, that would once again be 8. So this side I've already made 8, so I don't need to do anything to that side, but this side I need to multiply by 8. So what I'm going to do is I'm going to change the coefficient to 8. What that's going to do is it's going to do 8 times magnesium, which is 1. So I'm going to change my number to 8 there. And now I also changed my count now of iodine. So it's the coefficient times the subscript. So it's 8 times 2. So right now I have 16 iodines. So my magnesiums are good, my sulfurs are good. Now I need to worry about my iodines. So I've got 2 and 16, and the least common multiple is 16. So I need to multiply this side by 8 in order to, I need to multiply it by 8 in order to get it to 16. So I put an 8 in front of here. That 8 is going to distribute to that 2, which means it's 8 times 2, so I get 16. All right, so now it looks, just checking, I've got 8 magnesiums on the left, 8 on the right. I've got 8 sulfurs on the left, 8 on the right. I've got 16 iodines on the left, 16 on the right, according to my counts. But what I am going to want to do is make sure that this balances out. So how do I do that? Well, what I do is I like to just do a final count. So I'm going to look at my magnesiums. I've got 8 times 1, so that's 8. I have 8 on the right. That's good. Now I'm going to work with the next one, which is sulfur. So I'm going to have 8 sulfurs on the left. I'm going to go to this guy. That's 8 sulfurs on the right. I've got now my iodine. So I've got 8 times 2, so 16 iodines on the left. I have 16 on the right, so I'm good as far as my counts go. There are 2 options that you can do now in front of the S8, and you can either put a 1, which tends to be not written, or you can just leave it as a blank and it's an understood 1. Similar to if I had 1x or x. I could write both of them the same. We tend to write just x in algebra, but you technically could write 1x and it would be fine. All right, the next one, we're going to do our counts. So we've got initial count of 1 Na on the left, 1 Na on the right. I have 1 mg on the left. I have 1 mg on the right. I've got CLs. I've got 1 CL on the left. I have 2 CLs on the right. Okay. Now here is where one of my hints comes into play, and that is with your acetate. Okay, so I look at it and I see a polyatomic and it goes bing, 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 bing in my head. Oh, I see all these weird elements put together. Okay, do I see that on the right-hand side? Yes, I do. So what I'm going to want to do is I'm going to want to group it together. So instead of saying I've got 2 C's, 3 H's, 2 O's, I now only have that acetate. How many acetates do I have on the left? Well, that would be 2. How many acetates currently do I have on the right? That would be 1. So now what I'm going to do is I'm going to try to balance it. My sodiums look good because they are 1 and 1. My chlorines are 1 and 2. So I'm going to do my chlorines first, and the common multiple between 1 and 2 is 2. So I'm going to put a 2 in front of here. I always try to do my coefficients first, putting that in, and then changing my counts down here, because it tends to confuse people by changing the counts in the bottom before actually doing the coefficients. You tend to forget that sodium's number also changed. So sodium now is 2 times 1, so that would be 2. My chlorine would be 2 times 1, so that would be 2. So now I screwed up my sodium, so I'm going to try to fix it right away. So I'm going to put a 2 between 2 and 1. The common multiple is 2. So I'm going to put a 2 as the coefficient in front of NaC2H3O2. That 2 is going to distribute to Na, which will make that 2 because it's 2 times 1. And I only have 1 acetate here, so 2 times 1 would make that 2. All right, now I'm going to do my checks. I've got 2 NAs on the left, 2 NAs on the right, 2 CLs on the left, 2 CLs on the right, 1 Mg, 1 Mg, and then 2 acetates, 2 acetates. So I am balanced. Once again, you can put 1s in for these individual spots, or you could just leave them blanks. All right, combustion reactions. Combustion reactions tend to be the hard ones to balance. And you don't know exactly what a combustion reaction is right now, but you will in a little bit. And these always tend to be the harder ones to balance. So doing my initial counts, I noticed that there's 1 carbon on the left, 1 carbon on the right. There are 4 hydrogens on the left, 2 hydrogens on the right. There are 2 oxygens on the left, and there are 2 from this guy and 1 oxygen from that, so there's a total of 3 oxygens from that side. Now this is where, because of these combustion reactions, this is where it comes into play that you want to do oxygens last and hydrogens second to last. So because I'm doing oxygens and hydrogens last for everything, I'm going to do carbon first. So my carbons are already balanced. So my next one that I'm going to to try to fix is my hydrogen count. And I've got 4 on the left and I have 2 on the right. So what's the common multiple? Well, that would be 4. So I'm going to make 4 times 1 so I can leave it. Whereas on the right, I need to make this a 2 for my coefficient. Remember, once again, you can only change the number in front or the coefficient. You can never change the actual compound structure. So now I need to reevaluate my compound count. So I've got 2 times 2, so that would be 4. And I have 2 times 1 from this guy, so this would be 2. And then my other oxygen, I still have the 2 from that guy, so 2 plus 2 would be 4. Okay, so now what I'm going to do is I'm going to look at my oxygens because I've balanced everything else out. And my oxygens are 4 on the right, so how can I make them 4 on the left? Well, all I need to do is put a 2 in front of here. That changes that count to a 4, so I've got 1, 2, 1, 2 for my coefficients. All right, we're getting into the harder parts. So here we go. Initial counts, we have 2 carbons, 1 carbon. We have 6 hydrogens, 2 hydrogens. We have 2 oxygens and 3 oxygens on the right. All right, so once again, you want to do your carbons first because hydrogens and oxygens are always last. So I'm going to put a 2 in front of this coefficient. That changes that count to a 2, which makes my oxygen count 4 from the 2 times CO2. So that would be 4 from this guy plus the 1 from that guy. So that would be a total of 5. So my oxygen count has changed to a 5. All right, you still don't want to balance your oxygens, though. What you want to balance is your hydrogens. So what I'm going to do is I'm going to balance my hydrogens by, I know I need to multiply this guy by 3 so that this total equals 6. Now I'm going to figure out my new oxygen count because by changing that coefficient in front of the water, I also changed my oxygen count. So I've got still 4 from that 2CO2, and now I've got 3 from that H2O, so that's a 7. So now I'm going to try to find the common multiple between 2 and 7. And it doesn't usually turn out to be very easy for a lot of students. So here's where my hint comes. When you have an odd number of oxygens on one side, so 7, and an even number of oxygens on the other for combustion reactions, so 2, double all the coefficients except for the one in front of the oxygen, and then try to balance the oxygens again. So what I'm going to do is I'm going to double it. So this guy was a 1 in front of the C2H6, so a 1 times 2 is now 2. I'm going to leave that guy with the oxygen right here for right now. This 2 will become a 4, and this 3 will become a 6. So now what I need to do is do my recount, okay, and see how this works. So my recount is now I have 4 carbons on the left and I have 4 carbons on the right. So that is still good. I'm going to erase this so that you guys can follow along a little bit easier. As far as my hydrogen counts, I got 2 times 6, so that would be 12 hydrogens on the left. I've got 6 times 2, so that would be 12 hydrogens on the right. My oxygen count still is 2 on the left, and now I need to figure out my right side. So it's 4 times 2, so 8, plus another 6, so that is 14. So I'm going to cross that off and put 14. So now what's the common multiple between 2 and 14? Well, that would be 14. So I just need to put that as a 7 in front. So that would go, the whole problem would balance to have the coefficients of 2, 7, 4, and 6. This would also change this to a 14. I would highly encourage after you do these to check all your work. You should always know whether you're right or wrong. How do you do that? You once again do all of your counts after you have done your initial calculations. Okay, and think that you're right. So I'm going to do my carbons. My carbons on the left are 4. My carbons on the right are 4. So that's a check. My hydrogens are at 12 on the left. They are 12 on the right, so that is a check. They are 14 for oxygens on the left. They are 8 plus 4, another 6, so they are 14 on the right. So we are good to go. So I know that this answer is the correct answer. The other one that comes into play with the combustion reactions is when you have this weird OH as a part of it. And once again, I don't assume that you know what a combustion reaction is as of this moment. But a combustion reaction, just to let you know, always ends in CO2 and H2O as your products. Okay, so let's do another count so we can see how this is kind of like a little tricky. So we're going to put a 2. We have 2 carbons on the left. We have 1 carbon on the right. We have 5 hydrogens plus that 1, so 6 hydrogens on the left. we have 2 hydrogens on the right. We have, as far as oxygens go, we have the 1 oxygen from here and the other 2 from there, so that's a 3. And we have 3 oxygens from those 2 guys on the right. So once again, you always want to do carbons first because you want to do oxygens last and hydrogens second to last. So what I'm going to do is I'm going to multiply this guy by 2. So when I do that, that changes my carbon count to a 2. It also changes my oxygen count to a 4 plus a 1. So that means 5 now, so I have 5 oxygens. Once again, you don't want to balance oxygens next. You always want to do oxygens last. So I'm now going to balance my hydrogen. So what am I going to do? I have 6 on the left, I have 2 on the right, so I'm going to multiply this by a 3. So now I've got 7, or I'm sorry, I'm going to show you that. It's 2 times 2, so I've got 4 on that one. It's going to change that to 6, and I've got 3 oxygens from the next guy, so that is a total of 7 oxygens now. All right, so I have an odd and an odd, so that previous hint doesn't come into play, but here's the hint that I give you. When you have an OH as a part of your hydrocarbon right here, hydrocarbon means you have a hydrogen with a carbon, remember? So if you have an OH, then take that O out of the count for both sides. So what I'm going to do is instead of pretending that this O is a part of my count, I'm going to take away 1 from each side. So now I'm going to take away that 1. So that's minus 1O, and I'm going to take a minus 1O from my counts over here. So instead I'm kind of feign that I have 6 on this side and 2 on this side. In reality, I still have 3 and 7, but I don't want to change anything in this guy because if I change that, then I change all of the counts for everything else. So now I'm comparing 2 oxygens versus 6. And what's the common multiple between that? Well, that would be 6, so you need to make that a 3. So if I put a 3 in front of here, now my true counts come into play when I'm checking it. Okay, that should have made my 6. So when I'm truly checking it, I have 2 carbons on the left. I have 2 carbons on the right. Doing my hydrogens, I have 6 from that guy, and I have 3 times 2, so 6 from that one. Now my oxygens, I have 1 from this guy, and then I have 6 from this one over to the right. So that make a total of 7. As far as oxygens on the right-hand side, I have 2 times 2, which is 4, plus my 3 times 1, so that's 3. So I have a total of 7 oxygens on the right. Looking at this, I know that this is entirely balanced, so I am perfectly happy with this chemical reaction. All right, hopefully you kind of have an understanding about basic balancing of chemical reactions.